Betelgeuse or Beetlejuice. It's a red giant star. If you put it where the sun is, it would extend out to the orbit of Jupiter. It's very unstable. It's about to explode.
Investigating the mysterious Betelgeuse to its core, new research has uncovered phenomena that contradict our present knowledge of star activity. In addition to its gigantic size and impending supernova potential, scientists have been perplexed by Betelgeuse's erratic dimming patterns. This is an example of unusual stellar behavior as well as a star approaching the conclusion of its life cycle. Current astrophysical models fail to adequately describe Betelgeuse's complicated internal dynamics, which are indicated by its unevenly pulsating surface in contrast to normal red supergiants. A nebula of dust and gas is forming around Betelgeuse as a result of its incredible rate of material shedding, according to researchers. This stellar mass loss is significantly more violent and unpredictable than what is predicted by theoretical models for stars in its class. The results have far-reaching consequences, suggesting that red supergiant development is driven by unknown mechanisms. On top of that, strange magnetic activity on Betelgeuse's surface has been picked up by recent observations. This new field of inquiry could be affected by this activity, which could be affecting the star's mass ejection patterns and variability. Both the observed and predicted magnetic fields are more complexly arranged, casting doubt on the standard model of star magnetism. These new findings have scientists rethinking Betelgeuse's ultimate destiny. Although a supernova explosion is expected, the exact moment and type of this catastrophe are currently the topic of heated debate. The peculiarities of Betelgeuse's behavior suggest that it may not undergo a supernova explosion in the manner that is currently anticipated for red supergiants. Some have speculated that Betelgeuse's quirks may have been influenced by an outside force, such as a planet or companion star. This has added another layer of mystery to the situation. One possible explanation for Betelgeuse's sporadic dimming and mass loss could be the gravitational influence of a neighboring celestial body, which would deform its outer layers. In light of these new facts, Betelgeuse should be seen as a lighthouse for rethinking ideas about stellar evolution, not only a case study in stellar life cycles. Understanding the many outcomes of stellar development, especially in the last stages of life for big stars, may be facilitated by the star's distinctive features. Beyond being an astronomical spectacle, Betelgeuse's imminent supernova is a watershed moment that might reshape astrophysical theory. An extraordinary chance to examine the demise of a huge star in unparalleled detail could be presented by the energy emitted by such a supernova, which could be observed from Earth. Among the less discussed consequences of Betelgeuse's supernova is its influence on the local cosmic environment. Nearby molecular clouds may be stimulated to produce new stars by the shock waves and expelled material. With the potential to give light on the stellar lifespan, this process, called triggered star formation, could give rise to a new generation of stars. Important information on supernova explosion physics could be gleaned from Betelgeuse's light curve. Live observation of the explosion stages could either confirm or refute current predictions, particularly those pertaining to supernova nucleosynthesis's production of heavy elements like uranium and gold. This phenomenon has the potential to profoundly alter our knowledge of the distribution of these elements in the cosmos, which are essential to the makeup of planets and life. Possible detection of neutrinos and gravitational waves from the supernova is another promising area. The characteristics of dense matter and the dynamics of supernova cores could be better understood with the help of such discoveries, which could pave the way for new directions in multi-messenger astronomy. Also, the compact object that was left behind after the supernova could be revealed to be a black hole or a neutron star in its aftermath. Our knowledge of stellar remnants and the final phases of stellar evolution would be greatly affected by this result. Supernova Betelgeuse may have far-reaching effects on the interstellar medium, changing its chemistry and dynamics while adding heavier atoms to it. In the development of galaxies and planetary systems, this enrichment process is pivotal. Finally, the effect of a Betelgeuse supernova on Earth's ecosystem is an intriguing but hypothetical option to think about. While the star isn't close enough to cause any immediate danger, the brightened sky could have an impact on animals that sleep during the day and could have a domino effect on other ecosystems. With all these things at stake, the final supernova of Betelgeuse is more than just a spectacular sight. It is a paradigm shift with far-reaching consequences for the fields of astronomy and astrophysics. Thanks to its unparalleled sensitivity and resolution, the James Webb Telescope has revealed previously unknown complexities in Betelgeuse's behavior. Among the most shocking findings is the identification of finer features in the star's outer layers that had not been observed before. The observations showed that the star's breathing is caused by a network of big convection cells that move heat from the core to the surface. The complexity of this pulsation is beyond anything we have seen before. Its magnitude and brightness changes test our assumptions about star dynamics. And with James Webb's near-infrared capabilities, scientists have been able to see the dust production processes around Betelgeuse unfold in real time. Stars' roles in the cosmic dust cycle, which is necessary for planet formation and life as we know it, can be better understood through this process. A red supergiant's mass loss processes can be better understood thanks to the telescope's observation of material ejection from Betelgeuse's surface, which captured the birth of this stellar dust. Furthermore, Betelgeuse's magnetic fields yielded an unexpected finding. The James Webb Telescope has found intricate structures in the magnetic fields of these enormous stars, disproving earlier assumptions that their environs were rather basic. Based on these results, the star's magnetic field is probably affecting its pulsation behavior and is crucial to its mass loss process. Most intriguingly, Betelgeuse's expelled material shows indications of possible chemical complexity, according to James Webb. It was not thought that molecules and maybe even organic compounds could exist in the hostile environment surrounding a dying star. The nature of the molecules that can be formed in space and the chemistry that happens around supernovae are both brought up by this new finding. Better predictions of when Betelgeuse would go supernova have been made possible by the more exact observations of its size and temperature that the telescope has supplied. Models that attempt to foretell the lifespan of large stars rely heavily on these measurements. But that's not all Betelgeuse has to hide. After this first perplexing layer, there will be even more to peel back. Upon further inspection, what did we discover beneath its throbbing surface? We invite you to accompany us as we unveil a cosmos that surpasses our wildest dreams. Delving into the most recent observations of Betelgeuse made by the James Webb Telescope brings attention to the star's mysterious character and ushers in a new age of cosmic exploration, where every new discovery raises more questions than it answers. Among the giants of the universe, Betelgeuse stands out as an unmatched observational target for amateur and professional astronomers. At about 642 light-years from Earth, this star, which marks the shoulder of Orion, can be seen clearly even without telescopes. It is a bright, clearly reddish star among the stars. The fact that it is pulsating, which is not easy to see with the human eye, further complicates matters when studying Betelgeuse because it is not simply expanding and contracting in a regular rhythm like a heartbeat, but in an irregular pattern that has long baffled astronomers. This irregularity causes substantial variations in brightness over time, which can be observed with even modest amateur equipment. Using state-of-the-art observational tools, recent studies have shown that Betelgeuse's size is so dynamically unstable that its actual diameter can change by a factor equal to the solar distance to Mars. This discovery casts doubt on the stability of red supergiants and points to a very unstable phase of Betelgeuse's life cycle. The star's surface is also adorned with enormous spots, considerably larger than those on the Sun, which cause variations in the star's luminosity. These spots, which are regions of strong magnetic activity, further complicate the pulsation pattern of the star and attest to the tumultuous processes taking place within and surrounding Betelgeuse. A complex atmosphere surrounding Betelgeuse, consisting of gas and dust being expelled from the star, has been suggested by recent observations, adding to its mystique. This material forms a nebula around the star, which is a contributing factor to its changing sky appearance and raises interesting questions regarding the nature of mass loss in red supergiants. Overall, seeing Betelgeuse in the sky is a means to delve into the deeper secrets of stellar evolution. The throbbing red light provides a breathtaking panorama as well as a window into the turbulent life of a dying star. When stars like Betelgeuse burst into supernova, their cores collapse under the force of gravity, creating either a neutron star or a black hole, depending on the star's initial mass. This cosmic event is of staggering proportions and fundamentally changes the space around them, adding to the stellar birth and death cycle. One such outcome could be neutron stars, which are extremely dense remnants around the size of a city but have a mass larger than the Sun. Such objects display extreme characteristics such as strong magnetic fields and fast rotation speeds, which give rise to pulsars, which are electromagnetic radiation beams. A black hole can be formed when the mass of the collapsing core is large enough. This is an object with such strong gravity that not even light can escape its gravity. The region around a black hole, where matter is heated and X-rays are emitted before it is consumed, is a rich field for astronomical observations that shed light on the properties of gravity and high-energy physics. In addition to releasing elements heavier than iron into the interstellar medium, supernova explosions enrich the cosmos with elements formed in the core of the exploding star through nuclear fusion. These elements are the building blocks of planets, and by extension, life. The material ejected by a supernova mixes with the gas and dust around it to form molecular clouds, which will collapse to produce new stars and planetary systems. Moreover, the shock waves from the explosion might cause surrounding thick molecular clouds to collapse, which in turn can accelerate the formation of new stars. This process highlights the interdependence of cosmic events, where the death of one star ushers in the creation of others. Not only does a star's life come to an end in the aftermath of a supernova, but it also plays an important role in the cosmic cycle of matter, which in turn affects how galaxies evolve and may even spread the seeds of life throughout the cosmos. Regarding the possible consequences of Betelgeuse's supernova on Earth and our solar system, it is crucial to note that, despite the stellar explosion, the star's distance of about 642 light-years acts as a buffer, greatly reducing the direct effects. Nevertheless, the event will not be ignored and may have various significant consequences. To begin with, the supernova would be the brightest star in the sky for at least a few weeks, if not months, with estimates indicating that Betelgeuse could shine as brightly as a full moon, transforming night into twilight and making itself visible even during the day. This abrupt brightness boost could have an impact on nocturnal animals, changing their patterns of predation and navigation. In the past, supernovae such as SN 1054, which formed the Crab Nebula, and SN 1604, which Johannes Kepler observed, were near enough to be seen as bright stars in the sky from Earth, even during the day. Although these events taught us a lot about stellar evolution, their distance was too great for them to have any noticeable physical effect on Earth. Similarly, we can expect Betelgeuse's supernova to be a spectacular light show without any tangible threat to our planet. Supernova Betelgeuse, with its larger size and closer proximity to Earth, would certainly provide even more insights into the mechanics of supernovae, the formation of neutron stars or black holes, and the synthesis of heavy elements, providing an unprecedented opportunity for scientific study. The last supernova seen with the naked eye in our galaxy was SN 1987A in the Large Magellanic Cloud, a Milky Way satellite galaxy. Regarding cosmic radiation, a supernova must be located within approximately 50 light-years in order to significantly endanger Earth's biosphere by removing ozone and exposing the surface to dangerous UV radiation. Since Betelgeuse's supernova is more than 600 light-years away, it would not substantially raise cosmic radiation levels at Earth and hence would not endanger the inhabitants of that planet. Nevertheless, the supernova may produce unusual objects like black holes or neutron stars as its afterglow, which would provide a one-of-a-kind setting for astrophysical investigations. By studying these remnants, we may learn more about the stellar evolution of massive stars and the characteristics of these phenomena. If you thought Betelgeuse's pulsations were the pinnacle of cosmic mystery, get ready to delve deeper into the heart of stellar life and death, reads the Rehook. The tale of supernovae is waiting to be told, a story of immense creation and destruction. Are there any hidden meanings in these cosmic pyrotechnics? Shall we discover? The explosion of a star, known as a supernova, is one of the most powerful cosmic events that has ever occurred. Supernovae are important for cosmic evolution in many ways, including the distribution of life-sustaining elements and the influence on star formation. Two main types of supernovae have been identified, each with its own unique cosmic origin and cosmic implications. The Type I supernovae are those involving a binary star system in which a white dwarf star absorbs matter from its companion. When this white dwarf reaches a critical mass, about 1.4 times the Sun's mass, it collapses catastrophically and a thermonuclear explosion occurs. While this type does not greatly enrich the cosmos with heavy elements other than iron, it is a very useful tool for measuring cosmic distances because its peak brightness is consistent. At the end of their stellar lifetimes, massive stars that are unable to maintain nuclear fusion in their cores collapse under their own gravity, releasing their outer layers in a massive explosion that is a key process in the galactic synthesis and distribution of heavy elements such as carbon, oxygen, silicon, and iron. Depending on the star's initial mass, the collapsing core may transform into a neutron star or a black hole. At this point, Type II supernovae are born. Supernova explosions are known to produce heavy elements like gold, uranium, and platinum through nucleosynthesis, a process that is less often talked about but is essential for the chemical evolution of the universe because it seeds subsequent generations of stars and planets with the building blocks of life. Beyond the synthesis of elements, supernovae can compress interstellar gas and dust, a process called triggered star formation, which rejuvenates star-forming activity and guarantees that galaxies will continue to evolve and be dynamic. In addition, supernovae release vast quantities of energy into the interstellar medium, which heats it and enriches it with heavy elements. This enriched medium then serves as the substrate for the next generation of stars and planets. Supernovae play a crucial role in the cosmic matter cycle, contributing to an ecosystem where stellar deaths give rise to new astronomical objects. The study of supernovae also sheds light on the basic physics of extreme situations, such as how matter behaves under very high pressures and temperatures, how plasma shock waves work, and what neutrinos, those elusive particles that are crucial to the core collapse mechanism, are like. Learning about supernovae and what they mean not only fulfills our natural curiosity in the cosmos, but also sheds light on the processes that have molded the cosmic environment, revealing where all the materials that comprise our planet and ourselves came from. Betelgeuse, Antares, and the hypothetical Musaphie are three of the most interesting and massive stars in our galaxy, and they each bring something special to the cosmic stage. Betelgeuse, with a size of about 1,000 times the Sun's radius, is a red supergiant of enormous scale. Its luminosity, which fluctuates a lot and puts it in the top 20 brightest stars in the sky, is subject to large variations in luminosity due to its pulsating nature, which, in conjunction with stellar winds, gives the impression of a dying star with a mass of 10-20 times that of the Sun. With a size of approximately 700 times the Sun's, Antares is slightly smaller than Betelgeuse, but no less impressive. Its reddish glow and variable brightness rival and at times surpass Betelgeuse's, depending on their respective cycles of variability. Antares' substantial mass, about 12 to 17 times the Sun's, and its own significant mass loss highlight the diverse outcomes of stellar evolution among red supergiants. They are not to be overshadowed. Let us enter the domain of conjecture and think about Musaphie, a hypothetical star that pushes the limits of size and brightness even farther. With a radius of 1,500 times the Sun's, Musaphie would block the light from Betelgeuse and Antares, shining brightly enough to be seen across the galaxy. With a mass of about 25 times the Sun's, Musaphie would represent the upper limit of mass and brightness for red supergiants, illuminating the dynamics and variability of these cosmic giants. Investigating the histories and traits of Betelgeuse, Antares, and the hypothetical Musafir sheds light on the phenomenal variety and activity of stars in our cosmos. The disparities in magnitude, luminosity, and mass among these colossal objects in the sky serve to underscore the intricacies of stellar evolution, while simultaneously serving as a reminder of the dynamic, ever-evolving character of the universe. Thinking about what will happen to these stars makes us realize that every star's story is an individual journey, adding to the grand narrative of the universe, a narrative that persistently modifies our perception of the universe and our role in it. We have seen the diversity of the universe as we have journeyed from Antares to Musafir, but the question remains, what fate awaits our giant? The answer might transform our view of the night sky forever. Betelgeuse stands as a colossus amid stars, yet it is not alone in its cosmic dance. Stellar evolution is a complicated process that differs greatly with star mass. By comparing the projected fate of our Sun with Betelgeuse, a big star, we can see the different outcomes of stellar life cycles. Red supergiant Betelgeuse is nearing the end of its life cycle, which is characterized by a spectacular supernova explosion rather than a peaceful cessation of stellar activity. This catastrophic event happens when a star of this mass has used up all of its nuclear fuel and is no longer able to withstand the inward pull of gravity. In the case of Betelgeuse, whose initial mass was estimated to be 10 to 20 times that of the Sun, the core's collapse is inevitable, and a supernova will ensue, leaving behind either a neutron star or a black hole. On the other hand, the medium-sized Sun will undergo a considerably less violent death. It is now in its main sequence phase, gradually fusing hydrogen into helium in its core, and this process will last for approximately another 5 billion years. After this phase, the Sun will expand into a red giant, consuming Mercury, Venus, and maybe Earth. After this phase, it will shed its outer layers, forming a planetary nebula. What's left is a white dwarf, a dense cooling remnant of the star it once was, and it will gradually fade away over trillions of years. The Sun's future is very different from Betelgeuse's because of their starting masses. Massive stars like Betelgeuse have short lives and short deaths, using up their nuclear fuel much more quickly than smaller stars like the Sun. Their spectacular deaths enrich the interstellar medium with heavy elements, which helps to create new stars and planets. On the other hand, the Sun's gradual transition to a white dwarf will have less immediate influence on the universe around it, but its eventual demise will have a profound effect on the solar system, especially the inner planets. A knowledge of the stellar evolution of stars like Betelgeuse provides insight into the ultimate destiny of our Sun and shows how the cosmos is structured as a matter and energy cycle. The cosmic ecosystem relies on the recycling of materials that come from star and planet deaths, whether by supernova explosions or the shedding of planetary nebula. Looking at the evolution of these two very different stars highlights the variety of ways stars can evolve over their lifespan, all of which are subject to the same laws of physics but have distinct consequences depending on the mass they started with. These stellar behemoths, red supergiants like Betelgeuse, are among the largest stars in the galaxy, frequently exceeding sizes of 1,000 times the Sun's radius, and they play an important role in several cosmic processes as they are important stages in the life cycles of massive stars and significantly contribute to the chemical enrichment of the universe. Enhanced chemical content. The chemical enrichment of the interstellar medium is greatly enhanced by red supergiants because in their cores, nuclear fusion produces elements heavier than hydrogen and helium, all the way up to iron in the periodic table. When these stars explode in supernova events, they release these elements into space, where they contribute to the material that can be used to form new stars, planets, and even life. This process is fundamental for the evolution of the galaxy because it ensures that future star systems will have the ingredients needed for planets and possibly life. Manufacturing DNA. It is believed that the last stages of red supergiants' lives, particularly during supernova explosions, provide breeding grounds for the creation of even heavier elements through rapid neutron capture processes, adding to the cosmic chemical diversity. This is due to the fact that these stars' cores are so hot and pressurized that they are able to undergo advanced stages of fusion, which would not be possible in smaller stars like our Sun. Theories of stellar evolution. Our understanding of the evolution of massive stars from main sequence stars to red supergiants, and finally to supernovae or directly to black holes, poses new challenges and refines existing theoretical models that must account for mass loss, changes in luminosity, and the complex interplay of nuclear processes that define these giants' lifetimes. Red supergiants are an important benchmark for stellar evolution theories because their properties and behaviors shed light on this entire process. Controlling the creation of stars. Red supergiants are key players in the dynamic balance of stellar birth and death in the galaxy, and the supernovae that often mark their end of life have a significant impact on star formation in the galaxy. Shock waves from these explosions can compress nearby molecular clouds, which triggers the collapse of these clouds and the birth of new stars. On the other hand, these shock waves can disperse material, inhibiting star formation in certain regions. Aids in the advancement of knowledge. At last, red supergiants are scientific discovery machines. Research into them has pushed the boundaries of our knowledge of stellar atmospheres, wind phenomena, and the final stages of stellar evolution, while observations of these stars test our preconceived notions and inspire new tools and approaches in the field of astrophysics. Finally, red supergiants like Betelgeuse are more than just interesting objects to look at. They play an important role in the cosmic ballet of matter and energy, which impacts not only the chemical composition of the cosmos, but also the birth of new stars and planets. Astronomers are still guessing about what will happen to Betelgeuse in the long run, but one thing is certain. It will eventually turn into a supernova, a cosmic event that ends its life cycle as a red supergiant. With its present volatility and mass loss, Betelgeuse is on the edge of this dramatic transition, but when exactly it will happen is anyone's guess. Estimates for when its supernova will go off range from any moment now to thousands of years in the future. An unprecedented opportunity to study the mechanisms of supernova events up close will be presented by Betelgeuse's impending supernova explosion, which will have a profound impact on our understanding of the universe. Data from this explosion could either confirm or refute current models of stellar evolution. Observing a supernova from a star that has been studied in its pre-supernova state would be a first in modern astronomy, providing insights into the causes and sequence of events leading up to these explosions. Its supernova explosion will be so intense that it may be visible to the naked eye from anywhere on Earth, even during the day, providing an astronomical show not witnessed for centuries. For a while, it will rank among the sky's brightest objects, giving rise to a new star that will be visible to the naked eye everywhere. From a scientific point of view, the supernova will provide an opportunity for astronomers to observe the nucleosynthesis process, which is critical for understanding the formation and distribution of the elements necessary for life, as it occurs in real time as the forces unleashed in the explosion synthesize elements heavier than iron. In addition, the interstellar medium will be affected by the supernova shock waves, which may cause new stars to be born in nearby molecular clouds. This triggered star formation process is important for controlling the rate of star birth and star death in galaxies. On a larger scale, the heavy element enrichment of the surrounding space by Betelgeuse's supernova will add to the cosmic cycle of matter, which is essential for the construction of subsequent stellar and planetary generations, including those that may hold life. Rehook, we are on the verge of a revelation that could shatter the foundations of astronomy as our research of Betelgeuse and its cosmic siblings draws to a close. From this tale of the giant, what can we draw and how does it relate to to what is ahead in our own cosmic neighborhood. The last leg of our adventure will lead us to the deepest secrets of the cosmos. As we continue our cosmic tour, we enter the mysterious realm of Betelgeuse, a red supergiant star that has fascinated astronomers and the general public with its massive size and imminent supernova. Betelgeuse is a living example of the universe's dynamic and ever-changing character, as shown by its pulsating, breathing nature and its substantial contribution to the enrichment of heavy elements in the universe. Through comparison, we have seen how Betelgeuse compares to other cosmic giants like Antares and Musafi, highlighting the diversity and scale of stellar phenomena. We have also investigated the possible impacts of Betelgeuse's supernova, a cosmic event that is expected to illuminate our night sky with unprecedented brightness, providing a unique opportunity to study star life cycles and the formation of the universe's building blocks. Furthermore, we have discussed the larger cosmic implications of red supergiants, their crucial role in chemical enrichment, and their contribution to stellar evolution theories. What's more, we have been able to speculate on the timing and impact of Betelgeuse's supernova thanks to its eventual fate, which promises to add a significant chapter to our galactic understanding. As we wrap up this cosmic tour, it's worth remembering how magnificent Betelgeuse is and how it fits into the vast fabric of the universe. This giant story is far from over, and we can expect new questions and new insights into the mysteries of the cosmos to arise before its eventual supernova. If you've been captivated by the story of Betelgeuse and the boundless marvels of the cosmos, then you might want to consider subscribing for more content. Our cosmic adventure is far from over, and there are countless secrets just waiting to be revealed. Come along with us as we keep exploring space, looking for new insights, and deepening our knowledge of the cosmos. The next chapter will bring even more discoveries, and we can't wait to share them with you. To join us on another cosmic voyage, hit the like button, subscribe to our channel, and watch the video on your screen.